We're ready to start. Tomorrow, the test and the new lab that will start. Last week, we completed our first step in understanding how bridges work, and we saw that bridges, contrary to routers, are not configured. They are plug and play, and they get their forwarding tables by observing traffic, by learning the MAC addresses, the sources. They observe all traffic, so they learn from source addresses. And we saw that this is obvious in simple cases, but if there are multiple paths from one bridge to another one in the topology, then this may cause problems. Having multiple paths is something we usually have. We create what is called a mesh because we want to have some redundancy if one link goes down. And we will see how this is addressed in the, with bridges. Right. So here is a topology where there are multiple paths. For example, to go from switch or bridge, here is the same. Switch 7 to switch 1, we can go via switch 22 or the direct link. So there are multiple paths. The bridges take a brute force approach. They simply disable some of the ports in the local area network such that the resulting topology, the active topology, is always loop-free. And loop-free for that type of graph is synonym to being a tree. Right. So the bridges, by default, the ones you buy at Migros or other shops, will do what is called the spanning tree protocol. A spanning tree is a tree that spans all nodes. It's a graph theoretic concept. A spanning tree is a tree, a subgraph that visits all the nodes. Right. And hopefully is fully connected. How do they do it? Well, this is explained here in this algo rhyme. So this lady, Mrs. Radia Perlman, is the inventor of the spanning tree protocol. She also invented a poem to explain it. I will not sing it to you, although I would love to, but I will save you that this year. If you want to hear it sung, you can go to this link. But it's explaining here, least cost paths from root are traced. In the tree, these paths are placed. A mesh is made by folks like me. Then bridges find a spanning tree. So it's explaining everything. So let's go through a more less poetic description. So this is, the bridges do it in a completely self-organized way. So you buy 10 bridges, you connect them in an arbitrary fashion. When the bridges start, they will do that stuff. If you add an 11th bridge, they will do it again in order to create a new spanning tree. How do they do it? They do two things. One thing that's very easy to understand is to elect a root. So the bridges talk to each other and decide who is the root, who is the winner. And this is very simple. It's the one that has the highest label. So you give to every bridge a label, which is by default one of its MAC addresses, and you add to it a priority field. For example, if you want to say that this bridge that's in the middle, perhaps you would prefer this one to be the root, so you can orientate this, but the bridges don't know. They talk to each other. How do they do it exactly? When a bridge starts operating, it discovers other bridges, the ones that are directly on the same cables or the same wireless channel as itself. It doesn't discover all bridges, but it discovers only the neighbors. In this example here, switch 1 will talk to switch 7, switch 22, and switch 44, and they will exchange their labels. And after that, switch 1 will know the smallest. If we decide that the best is the smallest is 1, that's me. Right. Switch 44 will do the same. It will discover that switch 1, switch 2, and switch 22 exist, and the best is 1. So in a first step, every switch will discover who is the best of their neighbor. Then they will propagate this information. They will say to their neighbors not only who they are, but also who is the best neighbor, the best label that they've heard so far. So if this continues, switch 44 will inform switch 2 that it knows that the best label it has ever heard of is switch 1. So switch 2 will think, well, this is better than all the ones I've heard before. And if the network is fully connected and finite, so it's normal networks are, then this will stop in a finite number of steps. This is called a gossiping protocol. You learn about your neighbors and you repeat to your neighbors what you have heard. So in 1, 2, 3, 4 repetitions, you forward 1, 2, 3, 4 hops away from you the best you've learned. So that's fairly easy to understand. Then that's the easy part. Through that mechanism, the bridges know who is the root bridge. Then they do something smart, which is called using the distributed Bellman-Ford algorithm, that we will see in detail because this is used in another context. This is used by what is called distance vector routing protocol. So we will discuss in detail how this is done, but essentially using similar mechanisms as I've shown a minute ago in order to discover who is the best bridge. They will also discover what is the distance from myself to that best bridge and in which direction should I go towards to reach that bridge. This is what distance vector routing protocols do, and the algorithm that's behind that is Bellman-Ford. So by simply gossiping with each other, they will discover two things. They will discover who is the root. They will discover who is the root, and they will discover what is the distance to the root and in which direction they will go. Then they will mark the result of that in their ports by marking the ports that are towards the root as the root ports, the ports that are downstream from the roots towards the rest of the network. They call them designated. The terminology is a bit weird. This is explaining in detail how designated ports are exactly determined. And so essentially what they do, they decide for their ports which one are on the shortest path tree from anywhere to the root. That's one way to create a tree, by selecting shortest path. It's not the optimal one. There are better algorithms to find spanning trees, but this one can easily be distributed, can be made self-organized. And the ports that are not on the spanning tree are blocked. In the standard, they are called blocking here. So imagine you are bridges and you collectively run this thing. Question I'm asking you is, what will be the status of every port in this network here? Question here.
What if we find like two different paths with the same label for the route?
So the question is, what if we find several shortest paths to the same destination, which very frequently happens, right? We will see that in routing protocols, and when we will study OSPF, we allow this. We allow to have multiple equal cost paths. Here we don't, because we want a tree. If we do that, we have multiple paths. We will create loops. This is not accepted. So there is a tie-breaking rule in order to know if two neighbors have the same distance. If by going A or B I have the same distance to the root, I have to pick one of the two. By similar rules, as we had to elect the root, you pick one of the two ports that, for example, has the smaller MAC address. So you need a tie-breaking rule to make sure you find only one. Here's an example of a network. Of course, in order to find the shortest path, we need to put costs to the links, and the costs are done by the standard by simply looking at the physical layer, the bit rate of the link. So the higher the bit rate, the less the cost. So 10 gigabit per second link would have a cost of 1, and for example, a 100 megabit per second link would have a cost of 100 here, so that you make sure you will try to create a tree that is using as much as possible the high bit rate links. So what would be the result of the spanning tree protocol on this topology here? I'm proposing several solutions for some of the ports at switch 1, 2, and 3. So, of B3. So here we're zooming on B3. I have labeled 3 ports, 1, 2, 3. What is the state of each of those 3 ports when B3 and the others run the spanning tree protocol? And the majority says D. Let's see what happens. As human beings, we are very good at drawing shortest path. I mean, if I give you a map of Europe, and let's say we want to drive to Berlin, find a path, you will find a path that's probably very close to what Google Maps will find. We are less good at running a protocol strictly, so let's do that here. Here I've drawn the shortest path costs, I've drawn the shortest path tree, so the spanning tree is in red here. The root is B1, that's the one that has the smaller label. And then if I am from B4, for example, here is the shortest path from B4. It has a cost of 101. If I go the other way, there are two paths from B4 to B1, but that one is more expensive. So that is the shortest path. If we do that everywhere, we have the red shortest path tree. Now there's a tricky question. You could say the link between B2 and B3 is not used by anybody, so both should be blocking. It's true, except if this is a shared medium link here, perhaps you could insert here another thing, and like is the case here between B4 and B3. So this is what needs to be handled. So for that, the specification says that we need to look at all the local area links here and say what is the shortest path from here to there. And from here, the shortest path is this way. So this port still has to be open as a downstream port, as a designated port. So the 3 ports on B3 will be open, but on B2, this port will be closed because on this local area network, the shortest is via this way here. This is what the bridges do by discussing. So of course, B3 will not do what we're doing here. None of the bridges has the map of the entire topology, although they could create it by analyzing all the information, but they don't in principle. They just simply talk to the neighbors to decide what is the best way to go. For example, if we have this topology, that's a very frequent topology. When you create topology, for example, over a fairly large area, one very popular shape is the ring, because if you break any of the link on the ring, you still have connectivity. If you break any of the nodes, you still have connectivity for the systems that are not connected to the broken node. So it's it's simpler to manage than the previous topologies I've shown. What would the spanning tree produce in this thing? Well, we don't know exactly. It depends on the label, but the system is completely isotropic. It's the same in all rotations. So we'll pick one of the bridges and we'll disable one of the ports. This is what the spanning tree will do. Is it very smart? What do you think?
There is some traffic going from these 2 nodes, then we are overloading the spanning tree.
Exactly. So if there is some traffic going from A from those to this, for example, it will go the long way, right? So the only thing that the spanning tree does is, from the current topology that has perhaps some redundancy, remove the redundancy to find something that has no redundancy. Right? Of course, if that's the only thing it would do, it would be a bit stupid. There is still some benefit, is that it will react to any change in the topology. For example, if we break this link here, then the spanning tree protocol will detect, for example, this node will detect that so part of the spanning tree protocol mandates that the bridges ping the root to make sure the root is reachable. So this one will detect that the root is no longer reachable, and they will compute another path to the root, so a path that will go this way. So if this link breaks, after some convergence time of the protocol, this port will be reopened. So it will automatically adapt to losses of links or to deletion of nodes or addition of new nodes. There was a question? Yes?
Yes, where this time, if one link breaks, I assume that we lost traffic as the other less than the other port of the designated port.
If one of the links breaks,
it takes some time to analyze which one will be the designated port, and we may lose some traffic in that process.
So the question is what happens while we are repairing the loss of the link. So of course, during that time, things might go wrong. So during that time, at the minimum, some of the packets will be lost. In fact, with the spanning tree, there is worse than that. As we will see, in the MAC protocols require that there is always, there is no TTL in the header of MAC frames. Therefore, we must make sure there is no loop, even for very short period of times. So there is, in fact, a lot of delays that is added to, before opening a port, in addition to what I said, the bridges wait to be sure that the spanning tree has stabilized. So they will wait to make sure that all nodes are in a consistent state before reopening a port. So, and that adds some delay. There are variants of the spanning tree called the rapid spanning tree protocol, which uses exactly everything I said, except it is smarter in how it reopens the ports. It is able to detect that subtrees have not changed, for example, and reopen them very fast. In practice, it may take a good fraction of a minute to reestablish connectivity. Let me skip this one and move on to what I promised before. So I spoke of the Ethernet or MAC layer format. Here is one of the multiple formats. First, there are multiple physical layers. Every physical layer typically comes with a different Ethernet frame format. For example, Wi-Fi has a slightly different format. And even for Ethernet, there are two formats, one which is the most popular and another one. You have the details in the lecture note, but let's talk about this one. This is the minimal one. It contains destination address, source address, and a type. The type is saying what is contained inside this Ethernet packet, which is typically what packet? What do you carry inside an Ethernet packet? An IP packet, typically. So the type will specify whether it's IPv4, or IPv6. It's a different type. We find here again a symptom of the fact that IPv6 is not the next version of IP, it is another thing. It's different from IPv4. So it's a different protocol type here. So you have one number for IPv4, another one for IPv6. And then you would be surprised by seeing the huge number of protocols that can exist directly on Ethernet. Even though in practice today, most software and systems will use IPv4 or IPv6. We have seen already ARP. We have seen that ARP packets sent by IPv4 are not inside IP packets, so there is a special protocol type for ARP here. Then at the end, so this contains the payload seen from the MAC layer, which is typically an IP packet. And then you have, at the end you have something we'll discuss in a minute. At the beginning, there is something that is called a preamble and a start of frame delimiter. This is something that has to do with the physical layer. Ethernet transmissions are asynchronous. That means when you send an Ethernet packet, the clock of the receiver is not synchronized with the clock of the sender. They're not synchronized before you send. There's a fundamental problem in receiving bits in the physical layer, which is the clock. It seems fairly mundane, but it's very important. When a system writes bit into a channel, it writes it using its own clock, for example, at 1 gigabit per second. That means every nanosecond, it sends 1 bit. Right. On the receiver side, you have to read at exactly the same frequency. But now the clocks are not perfect. Even a very accurate clock has an accuracy relative to another clock, which is of the order of 10 to the minus 6, approximately, better or worse, depending if it's a very good or a poor clock. But even a very good clock that has an accuracy of 10 to the minus 9, that means the accuracy in the frequency, it means after 10 to the power 9, after 1 billion bits, it may differ by 1 bit compared to another clock. So after 1 second, they're already off, 2 clocks. Right? So any digital transmission needs to be synchronized. You need to read at exactly the same frequency at which you write. This is a very difficult problem in the physical layer. And since it's a difficult problem, there are ways to solve it that make it even more difficult or simpler. The more difficult system is to synchronize all the clocks of all the network using GPS, for example. This is what some optical carrier systems do. But Ethernet doesn't do it. You don't need GPS to run Ethernet. So what Ethernet does is it does not synchronize the clocks. In fact, the sender writes with its own clock, and the receiver will very quickly, at the beginning of the frame here, will sense the fluctuations. It will sense the sine or the multiple sine waves that are sent in the physical channel, and will use this information to lock its own clock using special circuitry called phase lock loop systems. So you spend some of the signal here to allow the receiver clock to synchronize to the sender. And while you're sending the packet, you will use that resynchronized clock. And when the packet is over, you will lose the synchronization and start it again by being silent. So between two Ethernet frames, there is always a short period where you send nothing to allow the clocks to realign here. So this is why we have this. Of course, this preamble and the start of frame delimiter, so the preamble is just random bits, and this is a pattern that indicates that's the end of the preamble. You will never see them when you do a wire sharing, because they are used by the physical layer to start detecting the signal. At the end, there is also a frame check sequence that we do not see either in Wireshark. The frame check sequence is an error detecting code. A code is some bits that we add to a signal to do things, typically to detect errors, for, in some cases, to repair errors. When you use RAID disks, all the data that are written to the disk are encoded such that if you lose a fraction of the data, you can recover them. Same thing when you send data, when you write data over a disk of any kind. Here, we do the same, except it's a very simple code. It is able to detect, it's been designed to work on very small bit error rates that we find typically on Ethernet, and it's able to detect isolated bit error rates. It can detect frames that have up to 3-bit errors. Right? So if you flip a few bits inside the frame, it will certainly detect it. If you flip a large number of bits, then, because the code has 32 bits, there is a probability of 2 to the minus 32 that the error that you created corresponds to a correct checksum. And so with probability that is given here, 2 to the power minus 32, so this is not e, this is 2 to the power minus 32, you will not detect the error. Yes?
Was it necessary to just state what is the type of the packet that is included in the link to frame?
So why do we have here? Why do we have a type here?
Yeah, shouldn't it be of the use of whatever is contained in the...
So the question is, why do we have a type here? Well, can you imagine how it would work if we don't have a type? So if we don't have a type, it means I give you a packet, and I don't tell you what it is. What is a packet when I give to you? It's a sequence of ones and zeros. Or if you want, you can write it in hexadecimal digit. So I give you a sequence of hexadecimal digits, and it's your job to find out what it is. It is possible. After all, that's what we do here. At the beginning, we have something that says this must be the beginning of a frame. So it is possible, but that means we would need to encode somehow the beginning of all packets by reserving some special patterns for all possible types. Now, this is not efficient in terms of compression. It's more efficient to have a few digits here that explain what is the type, and then get that information explicitly from here. It's something we will find practically in every protocol. Every protocol that is carrying some information carries the information of what is the nature of the protocol that it is carrying. So inside an IP packet, if you remember, there is something that says whether what is contained is a TCP segment or a UDP datagram or an ICMP message or whatever else. So we always have that problem at every layer. The most visible and important aspect is the address that we find in MAC frames. We have already discussed it. Most of the time when we use Ethernet today, we do this. We are connected by cables to a bridge that is also called a switch, and the switch will, using the learning method and the spanning tree that we have seen before, will forward the packet only to the ports that need it, at least except when it is learning. So once in a while, it may broadcast it on the spanning tree, but otherwise it will send only here. Which means that if you are with your packet sniffer here, you will not see the traffic that goes from A to R. Other systems that are truly shared medium don't have that property. The old systems that used share cables are promiscuous, so everybody can copy everything. And the wireless systems, if you're within range, also allow this. So we'll talk more about this. There are cable systems that provide this thing here. They are called concentrators. A concentrators is providing exactly this mental model. Concentrators are better for attackers. If you want to sniff all packets, it's better to do this. We have seen that there is one broadcast address, the all ones, in hexadecimal digits. So MAC addresses are often written in hexadecimal digits, sometimes lowercase, sometimes uppercase. It tends to be lowercase now. It was uppercase before. And the semantic of that is we send to everybody inside the local area network, whether the local area network is shared medium or not. At the beginning, local area networks were shared medium, so it made a lot of sense to have broadcast, because a broadcast doesn't cost more than a unicast frame in a shared medium thing. Right? In terms of usage of the channel, is the same. If you have bridges, here is the broadcast frames are sent along the spanning tree. So if one frame is sent, for example, from this guy here, it will be sent to all nodes along the spanning tree, here, to all ports along the spanning tree. There is a cost of being broadcast. You flood all the network here. Now, we are happy to have a tree when we do this, because otherwise, when we flood, if we didn't have a tree, we would have loops. And as you have noticed, there is no TTL in MAC frame. So loop at the Ethernet layer is fatal. If you have a loop, your network is dead. We have seen that IPv6 is fond of multicast addresses. Here is what happens at the MAC layer with multicast addresses. For some reason, multicast addresses are identified by the 8th bit. I think at the origin it was the 1st bit, but the processor tape us, depending on which processor you would write the words, Motorola or Intel, there are big Indians, small Indians. So to keep a long story short, at the end of the day, it's the last bit of the 1st byte, so the last digit of the 2nd hexadecimal digit. If it's 1, it means it's a multicast address, right? So here, 01, 3301. If the 2nd digit is odd, then it means it's a multicast address. So you should not have an adapter that has an address with a 01 something. Some of the blocks are reserved. For example, 3333 is reserved for IPv6 multicast. So this is necessarily an IPv6 multicast address. This is necessarily an IPv4 multicast address. For some reason, the blocks are not the same size. And don't ask me why, I don't know why. And there are some specific non-IP protocols that heavily make use of multicast, and they have some reserved addresses here. PTP is a timing protocol that you use. For example, if you distribute the time of GPS using Ethernet, you would use those multicast addresses here. Now, what happens if you have the idea of multicast is simple. If you have a shared medium local area network, if everybody receives, then the job of the software is to control the adapter such that if the host subscribes to this multicast address, the adapter will deliver the packets to the host here. Now the adapter, the hardware, the MAC layer, has to know whether a host is subscribing to a multicast address. There is no protocol in layer 2 to subscribe to a multicast address, so we have a contradiction here. We have multicast, but we have no protocol to handle it. What happens is that multicast is typically handled either by out-of-the-band information. For example, if you're a PTP device, you know that you run PTP, you've bought an adapter that is special for PTP, so this one knows by construction that it has to receive the PTP multicast packets. So here, there's no problem. If it's an IPv6 multicast, then the adapter knows by talking to the operating system, so it has to get the information from the IP multicast address here. The more tricky thing is what happens if you have bridges here. So non-smart bridges, so the bridges you would buy at Migros for 30 francs, they are still smart, they will run the spanning tree protocol, you can connect them in a ring fashion. They will create a spanning tree, and then what they will do, they will send all multicast packets as broadcast, which defeats the purpose of having multicast, but at least it works. Smarter bridges, well, they have a difficulty. Again, the absence of a MAC protocol, a MAC layer protocol for multicast makes it, in principle, impossible. If we are clean and if we say what is happening at layer 2 should look only at the protocols of layer 2. But the reality is a bit different. When Cisco builds intelligent bridges that they sell at a very high price, they will do lots of very fancy things that violate all the architecture. In software, you can do practically everything. You will not go to jail because a MAC layer software looks at the content of a TCP header, for example. If it's possible, you will do it. So what will happen typically is that those so-called smart bridges, they're not really bridges only, they do smarter things, but those smart bridges will sniff all the IP layer multicast things, and they will know whether, for example, an adapter has subscribed to a multicast group by looking at the IP layer information, and will pass this information to other bridges here using ad hoc protocols here. So it will typically use either the configuration from the adapter, or even we will see when we talk about multicast that there are protocols at the IP layer to decide who should receive a multicast packet or not. So the bridges will overhear those packets and will create their distribution tree with that here. Here is a Wireshark or pretty printed thing that I've done on a computer here. We see an Ethernet packet that contains an IP packet. We see that the ether type is indicating IPv6, so it's an IPv6 packet here. We see that it's ICMP because the next header, which is the protocol type of IPv6, is this. We see that the destination address is that one, FF02, which is a multicast address. And we see that the destination MAC address is 3333 FF01001 here. What can you say about the MAC address that is here? And the majority says B, which is almost true. This, I must admit, it was a tricky question. It's true that, the address that is here is the solicited node multicast address, which is derived from the last 24 bits of the destination IP address. But this is now, the question is, how is this derived from this IP address? So now this is an IP address. And standards say, if you have an IPv6 multicast address, you take the last 32 bits and you put it into the MAC address. So this, how do you get, the only tricky part is how do you get the last 32 bits when it's compressed? So the address is this one. Now you uncompress it, and you will see those are the last 32 bits. Here is 16 bit, here is 16 bits, so the last 32 bit is this one. So this is how you will expand it by getting the last 32 bits here. That's an easy one. The answer is A. Is B. Obviously. Last question. That's the question that is posed when you have bought your switches from Migros Electronics and you have upgraded all your stuff to IPv6. Do you need to upgrade your switches? That's the question. In other words, do you need to make sure on the box that it's IPv6 compliant for the LAN switches? And the correct answer is A. At least if you have switches that are not too smart. If they are very smart, they are IPv6 capable. There would be no problem. If they are dumb switches, they don't try to handle IP multicast in a smart way. So they will do the learning, the forwarding, and the spanning tree. And all of that has nothing to do with the type of packets that is carried, whether IPv4 or IPv6 or something else. This is very important. This is answering one of the questions that was asked 2-3 weeks ago. Why do we have IPv4, IPv6, and the MAC layer? Or probably the 3 is too much, but given that we have IPv4 and IPv6, it is good that we still have the MAC layer because of this, right? Imagine the MAC layer, the things you use to interconnect devices, they would be IP specific. Whenever you change from IPv4 to IPv6, you have to make sure that those devices support all kinds of changes you're doing here. So the MAC layer is completely independent of whether you do IPv4 and IPv6. And as we will see in a minute, we can do even other things, and it will continue to work in all of those cases. So this is reviving the interest in the MAC layer because we're now in this phase where IPv4 and IPv6 are coexisting. We are very often confronted to what is called virtual LANs. So virtual LANs is something completely bizarre and strange that was never anticipated at the beginning of the TCP-IP architecture and is where the logic of evolution leads to things that are less beautiful than originally planned. Now, the logic of evolution is that at the end, the less practical things should disappear. So perhaps virtual LANs will disappear one day. But today, here is what we have. Local area networks were used very often as more than simply a mechanism for interconnecting an extended physical layer, if you want. Because there are things like broadcast that work easily at the MAC layer that don't work easily at the IP layer. If you use iTunes at home to stream your music, it will work only within your local area network. iTunes is perhaps not so important, but although, who knows, in companies, you do similar things. You may have, for example, a finance department that has a number of documents, and those documents, they are accessible only if you're in the local area network of the finance department. It's a very poor way of doing things. If you want to secure your things, you should not rely on which LAN you're sitting on. But this is done. This is done. So that leads to things like, because the LAN, the local area network to which you're sitting, gives more information than we would really like to. For example, it typically says which group you belong to. Even at EPFL, this is used, for example, if we are in a given lab, LCA2, or in another lab, LSIR, you have access to different printers, different servers, different things, and typically there is access control. If I am in my lab, I can access the file servers and the printers of my lab, but not the file printers and of another lab here. So the way this is done is, at the origin, everybody was sitting at the same corridor. We were on the same local area network. Today, of course, this is not flexible. You would like to be able to move office, change office, and still be in the same local area network. That is the problem that virtual LANs are solving. Here I'm showing 3 virtual LANs, red, green, and blue, and 3 switches. But the belonging of which virtual LAN you're in is completely independent of where you're physically located. So we want, for example, that C, D, and G belong to the same virtual LAN, A and Y belong to the same virtual LAN, and X, E, F, B also belong to the same virtual LAN. So G is the anomaly, for example, here. So that's the guy in my lab, but there's no space on my floor, so it's sitting at an upper floor, but we still would like it to be in my lab. Again, this is not very smart. The right way to do things is to do a more secure control at the application layer and define who is allowed to use which printer in the printer software and by managing access control, not by saying you can access the printer because you're on the same LAN as me. But this is unfortunately done. How can that be done? Well, the idea is simply to add in the Ethernet frame a tag which is a 4-byte label number that indicates the number of a LAN. So if you do this, you need to have some software that will decide the red LAN at this number, and you will also need to say that C and D belong to the red LAN. So when you boot or through DHCP or other LAN management system, you will need to have a configuration server that will give that information. I'll just steal 1 minute of the break to conclude here. Now, if you are a host and you're sitting on a virtual LAN, you don't know that you're sitting on the virtual LAN. So if we do a Wireshark of the traffic that goes out of C, we will not see this label because there's no need to see it. C is connected to the switch. It's the switch that is configured to say when C connects to me, by looking at the credentials of who is C, I can know in which LAN, virtual LAN it exists. This is what you do in the morning when you come to EPFL and you connect to the wireless LAN of EPFL. You connect to one base station, and this base station assigns you to one virtual LAN. And then as you move through EPFL, for example, you were in the morning here, so you belong to the red virtual LAN for the entire day. As you move through EPFL, you will connect perhaps to a different base station, but you will still be in the same virtual LAN. In the case of wireless LAN, this has a benefit. In the case of Ethernet, this has a benefit which I claim is not so good. It's a poor security practice. In the case of virtual LAN, it has one benefit. Which one? If you came this morning through BC into EPFL, you had an IP address that comes from the LAN that's located at BC. When you come into this room, you are like the red guy here. You've changed. There are more than 1,000 base stations at EPFL, so there are multiple subnets. You probably are in a different subnet if there would not be virtual LANs. By being in the same virtual LAN, a virtual LAN is one LAN. So from the IP viewpoint, one virtual LAN is one subnet, which means you will keep your same IP address. So how do you manage all those virtual LANs? Well, Cisco does it by having very expensive software for doing that. Voilà, we'll do a break and resume this virtual LAN story in 15 minutes.